So thanks very much, and I'm going to apologize for using a very old form of German that was taken to the British Islands 5,000 years ago or something. It's called English today, and anyway, so please bear with me and appreciate your interest and your patience. And we're going to talk a little bit about sort of how quantum computing came to be, and we'll talk about the real father of quantum computing, and then a little bit about the state of the art, and then that should point toward Martin's talk about actually using quantum computing. And again, we said last night that Volkswagen has done is the first real application of quantum computing that you could explain to your mother, I think. In our case, quantum computing, or the ideas behind quantum computing, have been around for quite a while. They go back to many names that you'll know here in Germany, Max Planck, perhaps being electrocuted or something, but Max Planck, and then Erwin Schrödinger, Schrödinger's famous thought experiment about the cat, which we won't go into today, and even Albert Einstein, who helped form the theoretical basis for quantum computing, but then also didn't really believe in part of it. And he talked about, that spooky interaction at a distance. Don't know that I'm going to believe in that, and we call that entanglement. And in fact, have shown that actually works on our computers at a small level, not a huge distance across the universe so far. And basically, the idea with quantum computers is that rather than using a digital computer to simulate physics, we try to use physics to be able to do some computing. And the person who brought us that idea was Richard Feynman. In 1982 or so, he started talking about maybe you could use different principles of quantum mechanics to be able to create a sort of computer that would then be able to, use physics. Again, you could do simulation or computing. And so he was the one who really had the ideas for how quantum computing, at least set the seed. He really is the father of quantum computing, at least in most people's thinking about setting the idea for it. And Richard Feynman was at Los Alamos in the early 1940s, the mid-1940s, one of the big, what's become a national laboratory at the U.S., and he ran the computing group there in 1943 through 45. And the computing group were a collection of people, mostly women, who were running calculators, and they would run calculations or do computing over and over and over again. And in 1983, it was the 40th anniversary of the Los Alamos laboratory in the United States. I was there. I ran the computing division at the time at Los Alamos. I was quite young, and it was before I was retired so many times. That's a joke from last night. Feynman gave, as you could see or maybe not see, but his name is right here, he was the keynote speaker, and his talk was Tiny Computers Obeying Quantum Mechanical Laws. And that was the first time I had ever heard of the idea of quantum computing, was in 1983. And this was a big, huge colloquium. But then a couple of days later, Feynman and Hans Bethe, those of you who are from the physics community would know some of these names, Hans Bethe and Edward Teller and others wanted to see what modern computing was like at Los Alamos. And so I took them on a tour, and at the time we were the largest scientific computing facility in the world. And I'll always remember this. We were there in front of one of the Cray supercomputers, and I can't do his accent, but Feynman said something like, young man, someday all of these big Crays are going to be replaced by quantum computers. And I had only heard of quantum computers 2 days before, and I said something really notable like, wow, cool. Or, I don't even remember what I said, but that was the first time that I heard of quantum computers. And here we are, roughly 35 years later, and now they're starting to make their way into reality. So it's been a long road. And our friends from Rigetti are here, and IBM and Google and others are working on different incarnations of quantum computing. But what we'll embark on and show you is what is really the world's first commercial quantum computer. And interestingly enough, we're about 75 years on the heels of the world's first digital computer. And that, of course, was, as we talked last night, was the Z1 through Z4 from the Zusa family. So basically what we do with quantum computing or quantum computers, is that we try to use quantum mechanical effects to our advantage rather than fighting against them. In traditional computing, a quantum effect can cause leakage currents on a transistor. It can cause a bit to flip from a 0 to a 1. And those are bad things in the digital world, but we try to take advantage of those in our world. And we'll show you a little more about this picture in a minute, but this is what our quantum computer looks like. The computer itself is a chip that's at the very end of what looks like the Terminator's arm or a James Bond death ray kind of deal. So it's much different than what we're used to. And in the digital world that we're used to, the bits we use are binary. It's a binary world. A bit of information is either a 0 or a 1, and we want it to be one of those two. And those bits and words and other things that we manipulate and use are all separable. And then lastly, if we hit a barrier, whether it be on a transistor or if we're doing a search and trying to find the lowest valley in a mountain range, we have to put more energy in to climb the side of the mountain and look over, or put more energy into the transistor to be able to go over the barrier. And that's sort of how our digital world works. In our world, we use these three principles of quantum mechanics to try to do computing. And the first one is superposition, where we've been able to build quantum bits, so qubits, we'll call them, and those qubits, with the principle of superposition, are a 0 or a 1 and both simultaneously. So we start out in a superposition state where you don't really know what our bits are because they're simultaneously a 0 and a 1. And only at the end of each calculation cycle do we move them into a binary state and they become a 0 or a 1. That's the way our machine works. Entanglement, if you can imagine my 10 fingers plus the clicker here, are in the digital world are all bits. If we were able to get those entangled, then we could make coordinated moves through that landscape without having to communicate between the bits. So we use that. It's been demonstrated on our machine at some level. It's a big physics experiment to try to see if all of our qubits are entangled, so we haven't done that, but they're clearly entangled on the unit cell level, so we use that. And then the last quantum effect that we use that's maybe easiest to visualize in a second is quantum tunneling. So in our case, if we hit a barrier, whether it be a transistor or if we're doing a search, rather than having to put more energy in to climb over the barrier, we use quantum tunneling to go through the barrier. So you'll see how that works in just a second with our type of machine. So the idea came originally from Feynman, and then David Deutsch in the UK in 1984 wrote a paper on building a quantum Turing machine. And so that sort of set the stage for people thinking about architectures for quantum computers. And then that led to a collection of people working on algorithms for these theoretical quantum computers like Deutsch had outlined, including Deutsch himself. And probably the most famous one, or most notorious one, is Peter Shor's algorithm, and you'll hear about that because that's the one that promises that if you have a universal quantum computer that you could run this algorithm on, you could factor any arbitrarily large number. And that's either a good thing if you want to break all the cryptographic codes in the world, or it's a bad thing if you want to protect all the things that have been encrypted over the last 30 or 40 years. To my knowledge, no one has a computer that can run Shor's algorithm today. And I think it'll probably be a while before that could happen. But the point is, that's what people are, things like this are, people are either really excited about or really afraid of. And you could factor those numbers very, very quickly. So algorithms for theoretical quantum computers started to come along in the 90s. And when you build a computer, and I've been working in computer companies now for 30 or 40 years, something like that. There are two things you have to take into account. One is, what architecture are you going to use? And then secondly, how are you going to build the machine? qubits, the devices that you're going to use. And in our case, there are several different architectures that we'll talk about in a second, but on the device level, there are different ways of building these quantum bits or qubits. And this was an article from, and we'll make these slides available to everybody, by the way. This was an article from Science magazine about probably 6 months ago, and it outlined 5 of the ways to be able to build qubits. And I won't go into all of those, but the one that we use are superconducting loops. So we build qubits out of special little loops of metal. We use niobium, and those, we run them at very near absolute zero, so colder than outer space. And we're able then, by doing that, to be able to get them to be superconducting and get into a superposition state, so they're both a 0 and a 1 simultaneously. But several other approaches, and I think we have some friends over in Vienna who are working on trapped ions, and folks all over the world working on trying to create different forms of qubits. So that was a little tour of them. And then if you're actually then going to take those, whatever type of qubits you decide to build, and put them together into an architecture, the 3 main architectures that people are looking at today are the gate model architecture, and that's kind of the one, that's the theoretical one that was probably laid out in the mid-'80s and is closer to what Feynman was thinking. IBM is working on, has a research machine like that that's available on the web that you can use. 5 qubits, I think, going to 16 or 17 in the next iteration. Microsoft is working on a version called a topological computer. They're awaiting which is mathematically very elegant, but they're awaiting on the discovery of a particle called a non-abelian anion. And so if any of you have one of those, you should let them know. And it's, probably 20 years or something like that before you would see one of those machines. And in our case, we're using an architectural approach that is simpler, but is far different than what we're used to in traditional computing. And it's called annealing or adiabatic computing. And so the way it works is that if you could imagine the Alps, say, so mountains and valleys, mountain ranges and valleys, what our computer does is, using those 3 quantum mechanical effects, is 5 to 10,000 times a second, it finds, without adding or subtracting or multiplying, it finds the lowest valley or valleys in the Alps. And that's what it does. What it's really doing is going to a low energy state, and that's sort of the equivalent of finding a low valley in mountainous terrain. Of course, it's really an energy landscape. It's not really mountains and valleys. And it's a very complicated energy landscape, to which there are, in our case, if we have 2,000 qubits today, there are 2 to the 2,000th potential solutions in that. An unimaginable number of solutions that get searched through with each cycle, again, 5 to 10,000 times a second. Our type of machine works, is sort of think about energy landscapes and finding the lowest valley or valleys, probably. So it's also a little difference is that it's probabilistic. With a digital computer, you run a problem, and then if you run it again, you get the same answer. In our case, that's not necessarily the case. If the mountains are like the Alps, very steep, and there is one low valley, or a low lake in this case, you may end up at Interlaken. If you run it 1,000 times, you may end up at Interlaken, 906 times, and then 22 more times in another low valley, and so forth. But if the energy landscape is more like the Sahara Desert, you'll end up with low energy solutions all over the place. So the answers you get are quite different world, not deterministic like the one that we've come from. This is what the computer looks like. There actually are 2 boxes that contain them here. And the boxes are about 3 meters by 3 meters by about 3 meters high. And that big the computer is no bigger than your thumbnail. That's the computer, but it operates in a sort of an extreme environment that we'll talk about. And so this big box is like a Faraday cage, and it's to keep radio frequency emanations and other things from disrupting the quantum calculation. The box is big enough, it was designed by our team, so it's big enough that you can have 4 people inside at the same time working on the computer when we're assembling them. Over time, they'll get much smaller, so that I could have one in my Lamborghini in a few years. But so then if we opened the door and walked inside, what you would see is it looks like a a can of soup or something, but a giant one. And it's this cylinder is about this big around and 3.5 or 4 feet tall. And if we took this, that's a part of the container, a shield. If we took that off, we'd see a smaller one, and if we took that off, a smaller one, and a smaller one, and a smaller one. And those are all levels of shielding, and also there's a different temperature regime within each of those levels. And so we start at room temperature out here in that big box that we looked at, and then we're at roughly liquid nitrogen temperature here, and then all the way down to the processor, we're running at 12 to 15 millikelvin. And that probably means it's the end of the talk with the bells going off. With that, thank you very much.